To finish the discussion on electric potential, which is V, which is voltage, and before we get into looking at electric currents and circuits, what we like to do is like to talk about capacitors just because of their usefulness. And so this will be a real quick narration of the 2 pages of notes, and there'll be a Google form questionnaire to go with it, and that'll be the end of capacitors. A capacitor is basically 2 conductors, and we separate them by an insulator. And the reason we have to separate them by an insulator, because as we know, when 2 conductors are in contact with each other, they behave as one single conductor, which means charges will move and flow and spread out between the 2 of them. We don't want that. We want whatever's on one to stay on one, and same for the other. So we have to separate them by the insulator. And again, you can make this out of anything. You can make it out of 2 human beings hanging in the air. We're conductors, air is an insulator. But the most common one is going to be 2 metal plates. It's the most effective, the most efficient if we're using a capacitor for its desired intention. Now, what we're going to find is that the thickness of the plates doesn't really matter. So what you want to use is some kind of foil. And, we obviously are stuck with aluminum foil in our everyday lives, but you can take any metal, pound it into a thin sheet, and it's referred to as foil. You can have gold foil, etc. If I do a search on Google for the different types of capacitors, you see what you're going to notice is a lot of these capacitors are cylindrical. These are all the teeny tiny little capacitors that you would see inside the circuit boards that you have. This one right here is a little bit larger, so this is one that you might see in a physics classroom. The ones we have are baby blue and are rather large. They look like the size of a really, really large battery right here, this blue one right here. So there's a smaller one right here, this right here. This would be the size of about a D cell. So you notice they're all cylindrical. Why would they be cylindrical? If I want 2 metal plates separated, why would I want them to be in a cylindrical package? Well, remember, we can design them out of really, really thin pieces of metal, foil. So what do? You lay down one big sheet of foil, you lay down some kind of insulation, you lay down another sheet of foil, and what can you do? You can roll it into a circle, roll it into a cylinder, and then just slide it into a tube. So what I have here are really, really, really big plates that are laid out, rolled up, and slid into this little cylindrical package. So if I were to crack this open and look, I would see a spiral of 2 pieces of foil separated by some kind of an insulator. What do I have at the end? It's got 2 screws. One screw touches one plate, one screw touches the other plate. So that's how you would design them. That's how you would see them most notably. So again, you look through here and most of them are cylindrical because again, it's a plate that is made out of foil, rolled together, and then slid into that package. So that's why you see them typically as cylinders. The symbol that we use when we draw these out is simply 2 parallel lines. Even if you don't have a conductor made of 2 parallel plates, we still show it with 2 parallel lines and a space, a little gap here. And that shows that the charges cannot jump between that space. Now, if I put in all the electricity I could find, could I make little lightning bolts and shocks happen between these 2 plates? Yes, I can. But we typically use these under voltages that are small enough where we don't get electricity jumping between the plates. So if we continue down, what we do is we take some kind of a power supply. That's going to be our battery. And our battery is just an energy source. And what a battery does is it's a charge pump. It's slow and steady, and it just moves charge. It's got a positive side, and it's got a negative side, which means it has a high potential side and a low potential side. And charges will go from high to low. Now at this point I need to make a pause. As we mentioned in the past, all of our rules are based on what a positive would do. WWPD is what I say when we do this particular section. Even though we know that is inaccurate, that rule was made before we knew it was inaccurate, which means it still stands. So from here forth, we will consider positives as the movers. It's wrong. We know it's wrong, but we still use positives as the movers. So when I have an energy source like a battery, I have my symbol over here, a long line with a short fat line parallel to each other. This represents the positive side, this represents the negative side, so I've got a high and a low. The internal workings of the battery and the chemicals inside don't allow the positives to go from this positive plate over to the negative plate. So how do they get there? They got to take the long way around. So it's almost like there's a fence put up here. How are you going to get past the fence? You got to find the gate. The gate is the rest of the circuit, which I don't have one drawn here, but that's how you get around that little gate. And the positives will still get around to the negatives as long as you give them a path. The strength of this power supply is going to be measured in voltage. It's our potential difference. Your Duracells and your Energizers and all those batteries you like to use, unless it's the little square 9-volt battery, they have 1.5 volts. And if you look on the packaging somewhere, it will actually tell you that. So as we scroll down, the charges move when the capacitor is connected to the power supply. So basically, I have a metal plate connected with a metal wire to the metal positive end of a battery. That's one big piece of metal. They are going to share charge. Same thing happening on the negative. So my positives are repelled from the positive end of the battery, and that side of the plate becomes positive because it's all one big piece of metal. The positives get attracted to the negative end, so basically our negative end of the battery pulls positives off, and so this picture down here is going to be helpful. So what I have here is my positive end of the battery pushing away all positives. Since we just made this piece of metal bigger, it can push positives out into the wire and onto the plate. The wires are so small that we don't really acknowledge any charge that they have stored up, but they have positives as well. Here, positives, because we're talking about positive motion, get pulled off of the plate and attracted into the negative. So this negative sucks in positives, leaving behind the negatives. And so now what do I have? I have a positive plate, I have a negative plate. There's a space in between, so the charges cannot jump. And what we find is that the same number of positives on this side, same number of negatives on that side. In my picture here, I've got 5 plus signs, I've got 5 minus signs. Now, we'll discuss why in just a second, but we would say that the charge stored up on our capacitor, that's the job of a capacitor, store up charge. It took work to push all these charges out here, and if we remember, work equals energy. So our capacitor stores energy to be used at a later time. Now again, we'll explain why the number is what it is, but if I've got 5 pluses and 5 minuses, I would say that I have a charge of 5 stored up. So wait, I got 5 and 5, shouldn't it be 10? Or it's positive and negative, shouldn't it be canceled out 0? Well, we're going to discuss why it's not 10. And should it be 0? You are correct. 5 pluses, 5 minuses, this whole thing is neutral, but we have them split up. Since they're split up, I've got charges, I've got positives built up on one side and negatives on the other. So for that reason, we don't say that it is neutral, although technically the whole object is neutral, yes. Now what we find is that each charge is harder to move than the last. So once I put on one plus sign, the next plus sign gets repelled by this one, so it was harder. The third one gets repelled by 2. The fourth gets repelled by 3. You can see what's happening here. So by the time I get this fifth one on here, my battery had to push against 4 positives repelling back. So it gets harder and harder and harder. And so what we find is when you charge up a capacitor, if I had a light bulb in the wire, the light bulb gets really bright at the beginning, and then it slowly dims as we move fewer and fewer charges. We would have done a lab in class, but we don't have the ability to do that, obviously. Now, once my voltage between these plates matches the voltage of the battery, so let's say I've got a 9-volt battery here. Well, once this one reaches 9 volts, I have just as much strength as my battery, charges stop flowing. Another way we can look at this is as I push the positives out, 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 I gain the same amount of energy as this side of the battery because it's one big chunk of metal. I have the same energy on this side of the battery, one big chunk of metal. Remember from last week, we call the negative side 0 volts. So I got a 0 volts here and a 9 volts over here. So every piece of metal that is in contact with that has a 9-volt label. Over here has a 0-volt label. So we stop charging once the potential difference, our delta V, is the same. Now, once we've done this, I can disconnect these wires. These charges are stranded. They are stuck. They are going nowhere until we give them a path. So what do? We give them a path. So I've taken away my battery, and what have I done? I've replaced it with this little symbol here for a light bulb, the little zigzag symbol with a circle around it is pretty common for a light bulb. So now, what have we just done? We have given the charges a path. This right here is an insulator. It's a fence. The positives should jump over onto this negative plate to neutralize it, but they don't have enough. The space is too far, too much insulation, whatever. They can't take the shortcut. They got to go the long way around. And once you make a path, that's exactly what they will do. This one single positive goes around, goes through the bulb, lights up the bulb, ends up on the negative plate. Once I do that, one of those negatives is now going to be neutralized. So what I'm going to try to do here is take my little eraser. Hopefully I don't erase too much. So one positive goes and neutralizes that negative. And immediately after the first, the second one goes. Number 2 goes. And then number 3 goes. Number 4 goes. And number 5 goes. Think back to the question we asked just a few minutes ago. We said, what charge does the capacitor have? And I said 5. We said it's not 0 because the charges are separated. We said, well, we have 5 and 5. Shouldn't it be 10? The question is, how many positives just traveled through that light bulb? The answer is 5. The negatives are stuck over here not moving, so we ended up with 5 charges moving. That's why we call it a charge of 5 instead of 10. Now, right at the beginning, if I try to undo all the erasing that I did, right at the beginning, I have 5 positives all pushing. So the first positive that goes gets shot out really fast because there's 4 positives behind it, repelling it forward. The next one gets repelled forward, but only by 3, and then only by 2. And eventually there's only one single positive. Why does it move? Because there's one single negative over here attracting it. So what we find is that we get this burst of charge at the beginning, but then it slows down. So the charges move slower as the charge drops. And we would see that with a light bulb that gets dimmer and dimmer and dimmer. So scrolling down, our capacitors store charges on the plate. What's the point? Why not just use a battery? Because a battery never runs out, or at least certainly not as quickly as a capacitor runs out. Well, here's the thing. Your capacitor can push those charges very, very quickly, and it can do it all at one time. The battery is slow and steady, slow and steady, slow and steady. Capacitor is all at once. And so you will see these most notably, they're in all the electronics that you use and all the little circuit boards. If you were to take apart your Blu-ray player, if you were to take apart parts of your computer, if you were to take apart your calculator, you're going to see this little green circuit board. And you'll see little capacitors in there. But for us, when do you see the use of a capacitor? Number 1, you see it with a camera flash. Now obviously everyone uses their phone nowadays, so you hit the button and your flashlight just turns on. Old school disposable cameras, and every year in class I ask, how many people remember those? And everyone still raises their hand. So perhaps you still remember those disposable cameras. It may have been a Kodak yellow camera. It may have been a Fuji white and green camera. Maybe it was a CVS camera. I don't remember the colors of those. But there was a button on there. It showed a little lightning bolt. We recognize that lightning bolt as the flash button. You would hold it down and hold it down and hold it down until it lit up. What you were doing is charging a capacitor. There's a battery inside those disposable cameras. It used to be that as a physics teacher, I could go to CVS and say, can I get all of your old AA batteries from all of the disposable cameras? Because they just throw them in a big bin. And they go, sure. But anyway, you hit this button and it charges, 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 and you might, when you use those, you might remember hearing this high-pitched squeal that sounds just like something charging up from like a cartoon movie. What happens once you hold that button down for about 3, 4, 5 seconds? You're good. You can let go, and that capacitor is now charged up. And what do? You hit the button, and all that charge that took you maybe 3, 4, 5 seconds to store up goes through the light bulb all at once. And what do you get? An intense flash. If you have a nice camera, not just your phone, but a nice camera, there's a battery pack in there. And that works all the electronic equipment, but what it also does is it charges up the flash. You can't take flash after flash after flash. You have to give it a few seconds in between. The last one here is an AED. So the paddles that you use to try to restart someone's heart who has a heart that has stopped or that's unstable. And obviously we have the ones that we can now use as normal human beings instead of being doctors and nurses. The AED. And if we go to a movie scenario, lots of things wrong with the movies, but some things that are accurate is you'll hear them saying, charging, charging, clear. The charging is a battery pack powering up 2 big plates. Why not just use the battery pack? Because it doesn't shoot enough electricity all at once. It's slow and steady. So what do? We do slow and steady, build up all the charge on the plates, and then we release the plates all at once, and based on where we place the pads, that electricity goes through the heart. So things to remember for your capacitor: each plate gains an equal but opposite charge. Technically the total is 0, but we know that because it's separate, we don't say that. The charge is stored. Stored charge is typically a capital Q. We've been using lowercase q for things. Capital Q is stored amount of charge. We still measure it in coulombs. Capacitance is capital C. Look at the confusion. Wait, charge Q is measured in coulombs C, and now I have capacitance C. It's a disaster. Capacitance is the storage ability of your capacitor. It's measured in something called a farad, which is a capital F. That's not a force. Force is a variable. This is a unit, F. It's like I said, it's a total disaster. The only thing that's nice is voltage measured in V. V measures V. So our storage ability of a capacitor measured in farads. And remember, we can do microcoulombs. We can also do microfarads. 1 coulomb is big, 1 farad is big. And your capacitance only depends on the construction. Now, I can connect different batteries to my capacitor and store different amounts of charge, but the storage ability, the storage space, is the same. So if I connect a 1.5 D cell to a capacitor and charge it up, I'll store a certain amount of charge Q. If I connect a 9-volt battery, I'll store more charge Q. So it all depends on what I put into it using my voltage. I always say that a capacitor is like a milk jug. How much volume can your milk jug hold? You'd say it's a 1-gallon milk jug. What if I poured it out and made it empty? How big is your jug? It's still a 1-gallon jug. What happens if I pour out half of it? It's still a 1-gallon jug. So I don't change it. Now, what I put into it, well, that will affect, that I can store different amounts in that 1-gallon container. So if I take 1 cup of water and pour it in, that's how much I store. I don't store all up 1 gallon. What if I overflow it? It's still a 1 gallon. There's a limit as to how much it can hold. So if I come down here, your capacitance is going to depend on how big you make your plates. The bigger the plates, the more capacitance you have, the more space you have to store up charge. It's inversely proportional to the distance. So if the plates are farther away, if you look at a picture, and we have one right up here, look at a picture. When I'm charging this thing up, I know this is the discharging picture, but when I charge this up, this negative plate, even though the charges can't jump, the negative plate still attracts pluses. So let's go to the actual picture. So if I go to my battery, charging this thing up, my battery is pushing positives onto this plate, but at the same time, this plate is also attracting positives. So this plate helps the battery make this thing positive. This positive is going to push away positives here. So this plate helps this one become more negative. So the plates help each other become more charged. So the farther away I make my plates, the smaller my capacitance. And I can also change up the insulator inside. That's called the dielectric. I can put in air, I can put in paper, I can put in plastic or styrofoam or whatever. the better I make my dielectric, the smaller I can make my capacitor and still store large amounts of charge. And the capacitor doesn't change unless you build it differently, as I say, the construction. So all of those things are the notes surrounding our capacitors. The relationship between all of these is, at this point, we're not going to have to worry about this, but I'm still going to write it out here. The charge that we store up is going to be equal to the voltage that I apply from my battery multiplied by the storage space. So I call this one the home shopping equation, QVC, the home shopping network. Q equals V times C. So if I have more voltage with that same capacitor system, I get more charge built up. So those are capacitors. And again, you would use those with a camera flash. You might see them used with an AED, and they're also used in a lot of circuitry for other little things. They store up charge to be used at a later time. So go to the Google form questions, and there'll be a few questions pertaining to these notes right here. And that will be our weekly attendance for, I believe this would be week 7.